Hello everyone, I'm Yue Xinbian and I come from University of California, San Diego. Today, I'm really glad to introduce our work, Demand Response Model Identification and Behavior Forecast with OptNet, a gradient-based approach. Our motivation is to identify the demand response model and to see whether we can embed this model knowledge and achieve better behavior forecast. Well, first one, I want to introduce the background and motivation. In this work, we focus on the price responsive demand response. Price responsive demand response is a study that employs the interaction of the consumers. You can see the system operator will give the price signals and the DR participants can adjust their electric usage according to the time varying price. And this is one example. You can see the orange curve is a time varying price signal. And once the price signal is higher, then the demand will be lower and the price signal is lower, then it will increase their demand. In this way, the operators can design the price to meet the grid's needs, especially to avoid the system emergencies. So if we study this demand response study, we can help design the price strategy, promote the system reliability, and reduce the operating costs. If the system operator has no exact knowledge, then it will definitely increase the system's volatility. Also, another topic of interest is the price responsive behavior forecast. That is, given the history data, including the price signals and the history demand, can we forecast the demand in the future? Existing literature includes statistical methods, deep learning methods, and inverse optimization. However, the first two are black box models, which require a large amount of data. And also it will suffer from limited accuracy and poor general ability to unseen price signals pattern. And also for the inverse optimization, it might require different formulation for different demand response model. So our motivation is because we know the decision-making process of the DR participant can be modeled as an optimization problem. Can we encode this model knowledge to help us to forecast the behavior? The answer is two. First, I want to introduce our model. The objective is to minimize the energy cost and some personal disutility. The personal disutility is to model how the consumer is willing to increase their usage or decrease their electric usage or delay their electricity usage. And the constraints is some system constraints, for example, the physical device constraints and some comfortless constraints. And our goal is to identify the agent model and use this model to forecast the price responsive behavior. Next, I will introduce our approach. First of all, we denote G is our agent model. The objective is to minimize the energy cost and the personal disutility, where lambda is the price signal, Y is the demand, the decision variable of the optimization, for example, the electricity usage. And alpha 1, alpha 2 is a personal disutility coefficient. So this term is the personal disutility. And the constraints contain the equality constraints and inequality constraints. It is different if you use different DR models. The challenge is that we denote Y is a decision variable and Z is the mapping of the decision variable, which is the system observation, and lambda is the price. We can only get access to lambda and Z. While we want to learn all the parameters in the agent decision model, that is alpha 1, alpha 2, and A, B, G, H. In our work, we consider 3 applications. The first one is the battery demand response model. That is, given the past price signal, the battery will decide the charging power and discharging power. It is the optimization problem. They want to minimize the energy cost and the degradation cost. First one, they want to, the charging power and discharging power are within the power limits. And the second one is the energy constraints. In this model, the observation is equal to the decision variable of the optimization problem. And the second one is a building demand response model with the temperature dynamics. You can see, given the price signal, the building model will decide the indoor temperature, the violation of temperature, and the power schedule. In this model, we can see the power, that is the system observation, is only the subset of the decision variables. This is our optimization problem. It's want to minimize the energy cost and the violation of the temperature. Sigma is the temperature, so the first constraint is a temperature dynamics constraint. And the second constraint is a power limits constraint. And the third indicates the temperature violation constraints. In this model, our model agent wants to decide the power usage to keep the building's temperature within the comfortable bounds, while it wants to minimize the energy cost. The third one is an aggregator model with multiple responsive loads. We assume the aggregator model can model multiple responsive loads, for example, the refrigerator, the television, etc. However, we can only get access to the sum of the electric usage. The discomfort coefficients are different among different loads. That is the alpha KT. So it wants to minimize the personal disutility and the energy costs, while there are the power limits constraints and the equality power limits constraints. Recall that we only get access to price lambda and the system of the observation Z. We want to identify the model theta. In our work, we process this identification as an optimization problem. We want to minimize the demand response and predicted demand response, and where the y hat is a solution of our agent model. We propose our gradient descent approach. First of all, we initialize the model parameter. Second, we can compute the decision variable using our initialized parameter, and we can compute the observation accordingly. Then we can evaluate the loss function. And finally, we can update the parameter using the gradient chain rule. However, you can see the partial L, partial Z, partial Y star can be easily implemented, while the partial Y star, partial theta cannot be easily computed, since it is a gradient of the solution with regard to the parameter in our optimization problem. This is our agent model. You can see the objective is convex and the constraint is convex. This is convex optimization problem, and it is strictly feasible. Thus, the strong duality holds. In this way, we can write the KKT conditions of the optimization problem, and then we can get a derivative of the KKT conditions accordingly. Once we write the compact form of the KKT conditions, we can write the partial Y star, partial theta. We divide both sides with the inverse of K, and we can divide both sides with the learned parameter. For example, if we want to compute dy d alpha 2, then we divide both sides with d alpha 2. It gets this form. So the dy-dfr2 is the first row of this term. Next, I will show you some results. For battery demand response model and building demand response model, we performed 10 independent experiments. And experiments shows almost all parameters achieve really low error in 10 experiments. It shows our work can identify the model parameter accurately. And second, we use real world price in both the battery demand response model and building demand response model. We compare our method with RNN and MLP on behavior forecast. It indicates that our method achieve better performance on DR predictions and require less historic data. For example, in battery demand response model, our method can accurately forecast the behavior based on the time varying price signal, while the RNN and MLP use much larger data set, and it can only approximate the rough pattern. And for the building demand response model, the OptNet 1 indicates both the power and indoor temperature can be observed, and the OptNet 2 indicates that only power can be accessed. We can see that even if we get limited observation, that is OptNet 2, our method achieve better performance to forecast the demand response. For the aggregator model, we use synthetic random price signal. We compare our method with RN, MLP, and inverse optimization. Our experiment shows we achieve better performance on their predictions and require less historic data to train. You can see using 3,000 data, it is comparable with our method, while our method only used 50 samples to train. Also, we compare with different noise level. Our method maintain lower error across different noise level. We also perform sensitivity analysis about how different numbers of training samples can affect our performance. We can see with limited training samples, our method achieve better performance than both MLP and RN. And when the training samples gets larger, the data-driven methods such as MLP, RN can increase their performance. Next part is the future work. First of all, I want to have a quick discussion on existed methods. For the data-driven methods like deep learning methods, we can see RN performs better than MLP in dealing with the temporal structure data. However, our method consistently outperform. However, our proposed method consistently outperforms both MLP and RNN, especially under the limited data regime. And for inverse optimization, it also incorporates the model knowledge, so it can obtain better prediction under the limited data situation. However, it requires different formulation for different applications, while the data-driven methods like MLP, RNN, and our approach can be easily adapted to different applications using only price and demand response data. To summarize, our work developed a novel learning framework for the identification of the price responsive demand response. Our contribution is to encode this prior knowledge so we can achieve better performance to forecast the demand response compared with the baselines. Also, we propose to use a gradient descent to identify this agent model. It can process larger data set compared to the inverse optimization. It is robust to noisy data, and it can be easily adapted to different applications. Well, it also has some disadvantages For example, it can get stuck in local minimum if there are multiple local minimums. And in our work, we also prove the convergence for agent model with equality constraints. So we envision our future work, we can provide a more refined convergence analysis for agent model with the inequality constraint. Also in future work, we can leverage the structure of different agent models. And another interesting direction can be price strategy design, because we can identify the model. Maybe you can decide a better price strategy based on the identified agent model. And our work has many extensions in real world. Since beyond the examples in our work, our proposed methods can be applicable to identify demand response models of many other types. For example, the combined heat power systems, the residential demand response, and other applications. Thank you so much.